Hi, everyone. This is Prasoon Varshney from Simbot Dialog Management and Language Generation team. Um, so we start off with what the Simbot challenge is. We are one of 10 teams participating in the Simbot challenge hosted by Amazon. It's a challenge for embodied AI agents. And the goal for embodied AI agents for household bots is to be able to understand high-level natural language, convert it to low language instructions that are temporally ordered, as well as executable in an environment, in a simulation environment, ask for clarifications and resolve any ambiguities therein, and generate denials in case of inability to perform an action. For example, if there is a hazardous wire in the middle, then it should just say, I can't perform this action rather than trying to perform it. Our team is composed of two sub-teams, the dialogue management and navigation. We will be focusing on the bold parts because there's another Capstone team on navigation that takes care of the last four things listed here. This is just a scene of how the game looks like, and our deployment is as an Alexa skill on Amazon Echo Show devices, which is in the hands of users as we speak. Evaluation is based on 4 different metrics from Amazon sides. One is game score that you might be able to see on the screen on the game screen. Then a CX score, which is a Likert scale rating from 1 to 5 based on how satisfied a customer is by playing our game, and 2 other scores that have not been started using yet, but like goal completion rate just means whether we are able, how many missions we are able to finish, where a mission means all of these things, and sub goal completion rates means how many of the sub tasks in this list we are able to finish. So moving on to the vision of our project, the task landscape here encompasses 3 things: audio, language, and vision. We kind of sit bang in the middle. There are a lot of vision and language benchmarks like Alfred and Teach. And then there is work on audio and embodiment side where, embodied agents might look for sounds that are occurring in the room and navigate based on a sound. Here, in this case, we get ASR input from Amazon Alexa, and then we need to care about embodiment in terms of object affordances, like what are the actions that we can perform with an object, or we also need to care about robotic affordances, like in the sense of what are the actions that we can perform with our agent, and that basically puts us in pragmatic, grounded dialogue domain. And our intended users for this whole year of the Capstone project were, in the beginning, an internal team, and then Alexa customers sitting at Amazon. So at this moment, the game is available on Echo Show devices, and the simulated part of general availability for the game is completed, and the embodied part is something that is a wide research area where which encompasses how can we actually enable these robots in real world houses. Quickly going over changes from the spring semester. So in the spring semester, Amazon recommended to us the AI to Thor simulator, and in the fall semester we are now using a proprietary arena simulator. The main changes here are object states and object-specific reactions. AI to Thor used to have both of these, but Arena Simulator does not give us state tracking. We have to manage all of that on our own. And more importantly, on the dialogue side of things, in the spring semester, we were using a public teach dataset, and now we are using a proprietary action trajectory dataset. And the action trajectory data actually makes dialogue quite complicated in the sense of there are no timestamps or ordering within a session. This was provided in teach. There is no environment state provided. This was again provided in a structured format at various timestamps within the episode in Teach. And as you go through a game session, Teach also provided you a list of objects that were successfully interacted with at any given point of time. And this object list is not provided in the action trajectory data, which contains only utterance to small action sequences. So yeah, our fall development goals are basically adapting to these new changes and performing all those basic tasks of understanding language instructions, asking clarifications, and the main phases that we needed to pass were passing the Amazon skill certification, which basically just means them giving us an official recognition of like our skill is ready to be deployed on Amazon store, and then participating in the internal beta competition. We're happy to say that we were able to accomplish all of the missions. So quickly going over the milestones in the spring, as we talked about, we participated, like we basically worked with public data sets and simulators. And this semester, we reworked our models to work with proprietary Amazon data sets and simulators. Our like detailed milestones are available if you want to look at it. But here are the fall phases and deadlines by Amazon. So we have completed the first three phases in this fall, which was and most important, the recent one being internal Amazon beta period, where users were rating us on a Likert scale from throughout November, basically. This period started on October 31st, ended on 29th November. And we're happy to say that we completed that phase with #1 rank on the leaderboard. So here's a quick video demo of the game actually being played. Hopefully you are able to hear it. Okay, I have kind of prepared for this circumstance, so let's just look at the transcript because the audio is not working. In the whole video that we just saw, the exact transcript is in the first utterance, Nikhil basically says, go to the break room and find a bowl. But here's an ASR issue. The ASR input to our system was recognized as bull instead of bowl. And our verification module uses phonetic matches to actually convert it to bowl. Then the second utterance was pick it up instead of pick the bowl up, where our core reference resolution again resolves it to bowl. Third is that when the user then says go to the quantum lab, we use static knowledge bases to map things to the environment. And then place the bowl on the color changer. This is where our main generative model comes into picture, where for place the bowl on the color changer, we reason about that we have to pick the bowl up first, pick up bowl, then go to the color changer, then place it on the color changer. When we say press the button, there are actually 3 buttons on the color changer. So we ask we ask a clarification question in this case. And when the user actually replies red, again, an ASR issue occurs, and we noticed that our logs had bed instead of red. And in this case, we asked a question like, I couldn't understand bed. Can you please tell me the color again? And when the user said the color is red, we were able to complete the task.
So the next section, we look at some of the requirements for our system, starting with the functional requirements. We want our system to be able to understand the user utterances as coming from the Amazon's ASR. We want to keep the user updated based on the state of the system and what mission we have accomplished. So we want to inform the user. And in case of ambiguity, we would want to request for clarification and alternate instruction if the instruction is not feasible. And in case of any adversarial command that might end up affecting the bot or damaging the environment, we would want to deny such commands. Here's the system where Simbot lies in the center of it, and the commander gives us the instruction where the Simbot interacts with the user and asks for clarification and give the task update. We have the environment where we get the egocentric observation and perform the low-level actions on it. Here are some of the non-functional environments like adaptability. We want our system to be able to adapt to different users and different types of user utterances. We want the user experience to be good. So we want the interface to support all categories of users, especially those with the special needs. Since it's a budgeted competition, we would want our system to perform well with the given cost constraint. And we also want our system to be able to complete the tasks that are being asked to complete and have a good success rate. These are some of the resource requirements. So the data is provided by Amazon as Amazon's action trajectory data. And on top of that, we generate some synthetic data to train and fine tune our models. We are deployed on AWS, and we have different types of AWS instances for different components of our system. And we have some Alexa show devices given by Amazon for testing and deploying our system. And some of the non-deployment human efforts are we are closely collaborating with the navigation team, and we effectively interacts with the Amazon team to debug and simulate related errors. And these are some of the risks that we see, like business risk and finance risk.
All right, so with this functional and non-functional requirements, let's see our holistic system design. So first, let's see how our project is integrating with the AWS and Alexa for the competition. So the whole flow is the user will use the Echo device and see the images and use the utterance instructions with Alexa. And the Alexa will have the AirSound modules that translates the audio into text and give it to the Arena application. The Arena will give the text utterance plus the images from the simulator to us. And we will give the prediction based on the text and the images with the sequence of actions to execute in the Arena application. And then in the end, the Arena will give back the visual results plus the response from us to the Echo device and to the users. So with the action sequence inference, so we're developing the action sequence inference server. So the whole flow looks like this. We have the utterance and the images, and we use the natural language understanding module to translate into the list of action and object pairs. And we'll give it to the navigation team, and the navigation team will process it and also execute it on the Arena server. And if it succeeds, we'll give back we'll use the natural language generation module to give back the response to the users, like down, what's next. And if it doesn't succeed, we may ask clarification questions to the user, like when we need more information, like what is the color of the bowl, for example. And our team specifically, and let's take a look at the data tier design on our team. So we use the DynamoDB to keep the state of the sessions. So the whole project is the whole module is stateless. The user will give us the utterance and images without the states of the session. So we use the DynamoDB to keep the text and to keep the history of the session. So we have two tables mainly. The first is dialog history. So that keeps all the dialogues before within this session. So for example, the user said pick it up, and we can know the historic session is to go to the apple, down, and then pick it up. And the other table is logs. So we keep the outputs, inputs of every module within our project to the logs, and we can use this log data to do the data analysis and error analysis. And our team focused on the natural language understanding part, and it is composed of multiple models. First, so let's check it one by one. So we have the utterance, and then we use the toxicity check to check whether it is a toxic or toxic utterance or instruction. And if it passed that, we use co-ref resolver to resolve the co-reference within the sentence. And we then pass the whole sentence to the several models. The first is first responder, which is basically a rule-based module. And then we use a model-based generative model to translate this into a sequence of shorter instructions. And then we use entity recognition to make it into a list of tuples, which is composed of actions and object pairs. And then we use the similarity and synonym mapping to map the objects, actions and objects that from the user's instructions to the actions of the objects that is defined within the game environment. So we use the knowledge base to keep all the actions and objects within the game environment. And we use the verification module to verify whether the actions and objects make sense. For example, if we're picking up a table, but we cannot actually pick up a table within the game definition. So we use the verification module to eliminate all the action object pairs that doesn't make sense. And then we output the list of the tuples to the navigation team and to execute the actions.
Next, we're going to dive deeper to the system components. First, so toxicity detector is a module that is designed to cope with toxic and hazardous instructions. And the goal of this component is to filter out them in the early stage so that they will not be they're not flowing into the downstream major parts of the system and attack the system or cause any unexpected behaviors. So for example, the true positive cases would include pick up the knife and kill yourself, or break yourself with a hammer, or some insult kind of things. But actually, there are a lot of off-the-shelf models for toxic detection. But the problem with them is that in our domain, there are a lot of instructions that actually include, as shown here, some very dangerous objects or predicates. And empirically, we find that these off-the-shelf models will classify these instances as positive based on the occurrence of these objects and predicates. And that's why we propose to instead train the model with a mixture of both the out-of-domain toxicity detection dataset and in-domain instructions, where we would label the in-domain instructions as negative instances. So for the data itself, the out-of-domain toxicity detector data, we choose the Jigsaw challenge data, which is a data set that's specialized on finding the unintended bias in toxicity classification. And the instances would include not only the toxic utterances, but also identity attack and sexual explicit contents. And we find that to also align with our end. So for the training data, we sample 10,000 instances from the out-of-domain dataset and over 4,000 of the in-domain instructions that we label as negative. So the model backbone is a Albert model, which is a light-weighted model that is, and we take the checkpoint that is pre-trained on the challenge itself. And for evaluation, we show 4 of the evaluation data coupled with the model's current predicted score. And we can see that for both the 3 categories of the positive cases, the model is able to assign a very high score, whereas for the other is pick up the knife, which is actually an in-domain safe instruction because it is not instructed to let the robot hurt itself or hurt anyone else. It is assigned with a very low score, so it is functioning as expected. And we've also statistically evaluated all the other training instances in the trajectory data and find they're all below the threshold of 0.2. So it's safe to conclude that this model is working quite well.
So the next module that we have is co-reference resolution. If the utterance said by the user passes the toxicity check, we send it to this co-reference resolution model. For this, we directly used a pre-trained ANIL NLP co-reference resolution model, which uses a spanbot internally. It worked pretty well for our use case, so we didn't explore any other models. Here is an example utterance and how it was processed. So if the user says, pick up the bowl, open the fridge, keep the bowl inside it, keep the bowl inside, close it, and after keeping that. So initially the model is gonna output spans of indexes of different words, and like it will also produce the grouping of these spans. Then we replace these indexes with the actual words and produce clusters, which is the third box here. Then we find out the longest noun phrase within each of these clusters. So in the first one, it's the bowl, and in the second one, it's the fridge. Then we replace this longest noun phrase with every other occurrence within that cluster in the original utterance, and then like send the scoref result, dialog to the next module. So an important thing to note here is that if we are not able to resolve any of the pronouns or any of the any of the non-noun phrases, or if like any of the clusters doesn't have a noun phrase to begin with, then we allow the later modules to handle such cases. We directly send the pronoun or any other non-noun phrase instance to the later modules. Later on, we'll see like how our generative model also tries to process this in case our co-reference resolution model fails. So here are a few of the qualitative results that we tested our model on. So the first one is just a simple case of noun phrase and a single pronoun. The second one has multiple noun phrases and multiple pronouns, and like each of the each of the pronoun refers to a different noun. So the first is successfully resolved to bowl, and the second it resolves to microwave. We found out through our analysis, like it is the most common pronoun that we found, but like it also worked on other pronouns like that, this, etc. We also tested cataphora, in which the pronoun comes before the noun itself in the original utterance. So in this case, like the sentences, can you pick it up the cake over there? It gets resolved to the cake. And this is the example where coref resolution is not possible because we have incomplete information. So if the utterances go to the quantum lab, and please get that from there, we don't know what that is. So we just resolve there and let the generative model handle the later part.
Yeah, so one of the most important components of our system is the action sequence generation. Given like a high level instruction, we have to like break it down into a sequence of low level instructions, right? So when the challenge started, we just had like a very baseline model that was given by Amazon that just used like regex to parse instructions. And the first model that we implemented on top of that was a simple grammar model. As we progressed through the competition, we learned, and we actually augmented this grammar model with actually a waterfall of models involving a semantic role labeler and a generative model. But again, all these three models were working like one after the other. So like if the first one fails, then we go to the second and third and fourth. And the final architecture that we now use is what we call as a unified architecture, where all these three models work in tandem. And we really, by having this unified architecture, one of the most important things that we have been able to do is cut down on a lot of latency issues of having to run through multiple models, and also improve upon the precision of at which we generate the sequence of actions. So now I'll walk you through the older models. So the first model was the grammar model. So what we had was a simple pause tagging model, which looked at the verbs and the nouns in the sentence. And based upon that, we used to map the nearest verb to the noun. So what used to happen is, like, suppose we had very simple utterances like go to laser. It used to work really well because we had the verb and the noun very close together. And what we found was that this model performs well on instructions which are granular and which have like a single verb and noun. But now if you make the instructions more complex, like for instance, if you say put the control panel into the laser, so now you will essentially be mapping put to control panel, or you will be mapping put to control panel and put to laser. But and if you resolve these, then you'll get place control panel, place laser, for instance, place being the synonym closest to put. But this is not an expected action sequence, right? So this is where we saw that whenever the instructions are incomplete and they're not granular enough, that is the places where the grammar model fails. Another problem with the grammar model was especially things like fire the laser using the laser monitor, because pause tagging essentially is not accurate at all points of time. Fire sometimes come as a noun to us, and hence we were not able to even identify what action was requested by the user. So this is the reason why the grammar model didn't work. And hence, when we went, we had to, to address like a part of the issue, which was, as we saw in the previous instruction, like plug the control panel into the laser cannon. What we had was we developed a new model, which is a deep semantic role labeling model. What this model did was, given an utterance, it extracted the verb and the context that was associated with that verb. So for instance, plug, and then the context that is associated with it is the control panel and the laser cannon. And then once we knew that we had like the verb and the context associated with verb, we could just like parse the context and see which templates the context maps to. And we defined these kind of generic templates like verb placeholder 1, placeholder 2. And then if we found a similar kind of template using semantic role labeling, we resolved it using our template resolver. So again, like in this case, it was resolved to pick up placeholder 1 and place placeholder 2. So, well, this solved, the second kind of issue that we described, which is it handled a lot of incomplete instructions, and it also allowed us to pass the skill certification without much difficulty. But again, could we do better? And where does the SRL model fail, right? So the first case where we saw was, so if we had like something like turn on the freeze ray using the monitor, which is like a causal sentence, if using templates, turn on would be mapped to freeze ray, and then using computer would be probably mapped, like using a monitor would be mapped together. And templates, when they get resolved, they would like result in like toggle freeze ray and then pick up monitor, which you can't really do in the environment. Hence, one of the things was that the SRL model, although it's good at extracting parts and templates, it does not have any implicit understanding of the environment, and it also cannot add information on its own, right? And then another case was, so suppose we had a template like, suppose we had an instruction like take the soda can to the shelf. Again, for templates which it had not seen before, it couldn't see that it has to like go to the shelf after it picks up the soda can, right? So again, it didn't know how to handle the unseen templates. And some cases like press on the red button. Here in this case, SRL just failed to identify press as the action verb, and that's why again this was kind of failing. So we kind of uh, these were the major drawbacks, and that's why we now involve like a more involved model, like which is a generative model, which should be.
So in the first version of our of the generative model, we actually use the Amazon trajectory data, which is an utterance, an instruction coupled with a sequence of actions where the action, for each action, we have different components. For example, the predicate and the object and the attribute of the objects. And we verbalize, we only care about the predicate and the object in this stage, and we verbalize the on these action sequence into like a textual form of actions. So we use a sequence to sequence model, which is the implementation is a BART model between on CNU data mass summarization data set. And we did a sanity check kind of things. We took 7K examples from the trajectory data, and we achieved the word error rate of around 12. So the reason why we use the word error rate here instead of the blue score is that the labels here are of canonical form, and we care about the ordering. And for machine translation, we will have different translations for the same input. But in this case, we have only one. But the problem with this module is that it's in the data itself. So the label of the trajectory data is conditioned on modality other than the language, for example, the vision and environment, which are not present in the data itself. And that will cause us a whole list of consequences. For example, spurious correlation among like locations and objects and instructions and actions. And we also have hallucinations that are caused by information mismatch between the training data and the training label, because the information of the labels are relying on other information. And also we have information loss because we are not taking account of, for example, the attribute of the objects. And for example, these problematic data instance would include find and take the apple slice and was able to go to desk, pick up apple, but desk is not there, it's in the environment. And approach the desk is labeled as go to computer because in that environment, computer appear together with the desk, but this is not the universally correct case based on the textual information. And for example, place the floppy disk in the computer on the red desk. So the place predicate do not have two objects associated with it in the trajectory data. This is very problematic. So we actually analyzed some of, actually we took out some of the examples and manually labeled them with a new labeling scheme where we would like to maintain the information as well as make the label only staying true to the textual information. So two of the problems would be that is able to be resolved by the new labeling scheme would be reference resolution within the sentence. And like we are dealing with composite verbs or structures using new predicates that would take binary operations or redundant actions. So these are the seed patterns that motivates us for the next stage, which is the construction of the template-based synthetic data. So here we present some of the analysis of the previous version and the current version of the model. So these are the predictions from the previous version, which is the model trained on the trajectory data, and the current model, which is trained on the synthetic data. So, for example, for the first utterance, the takeaway is that the model is able to deal with the predicate place that takes into objects and also deliver the attributes of the objects to the downstream components. And the takeaway from the second utterance is that it resolves the hallucination problem. And the third thing is about, so the trajectory data doesn't deal with navigation-based objects, and we wish to include that as well. So in the synthetic data, we also include navigation object actions. Yeah. So for the quantitative analysis, we only analyze the new version of data. So the evaluation is conducted on the data that is of the same distribution with the training data of the. So they are all part of the synthetic data, and we report the exact match ratio and the word error rate on these data, and we list 3 of the main templates. And we can see that at least on synthetic data. So for this unit testing, it's safe to conclude that this model is behaving reasonably well on the in-domain data.
All right. So as Shubham mentioned in our old models versus new models, and Shinwei also mentioned in our in generative model revamp 1.0 versus 2.0, we resolved a lot of our issues using synthetic data generation because of the lacking qualities in the Amazon's action trajectory data. So let's take an example. In these 2 visuals, in one case, an apple is placed in a fridge, and in another case, an apple is placed on a table. In the first environment layout, the action sequence for the input utterance, let's grab the red apple. The canonical action sequence of open the fridge, pick up the red apple, close the fridge makes sense. And in the second layout, go to the table and pick up the red apple makes sense. They're both correct in their respective layouts. And the problem with the Amazon's action trajectory data is exactly this, that they provide the action sequences in some environment, but which environment was it provided in, that information is lost. And so our generative model should not be very sensitive to what environment and a training instance was provided in. So that's the reason we wanted to create synthetic data, where we should only stay true to the utterance, like we should retain all the information in the utterance, as well as at the same time not hallucinate. So the ideal canonical sequence for this should just be pick up the red apple. So for synthetic data generation, we look at 6 different types of placeholders: actions, objects, attributes, locations, magnitudes, and directions. During synthetic data generation, we also take object affordances into account based on the environment. And a key design decision that we made was that for actions, we encourage the model to reason, but for every other placeholder, we encourage copy mechanism. The way this is done is that we have a big static knowledge base of action synonyms and object synonyms. So for actions, we actually replace the right-hand side or the generative model output training instance with its actual performable action, executable action. But for every other thing, we just replace it with its variation or synonym to encourage the model to just copy it. And later on, a verification module handles the synonym to actual object mapping. So here are some examples of the templates that we use to produce the generative data. So in the first case, we are saying use any action that is not equal to place, use some color, and then use some object that maps with the action place. And the second generative model template would just be very similar because it's a very simple instruction. In a more complex instruction, like the second one, where it's place a pickupable object on a receptacle, we generate something like pick up the pickupable object and then place it on some receptacle. For example, if the original utterance is set down soda can on a table, again, we encourage reasoning over action. So set down gets converted to pick up, which is an executable action. And we encourage copy mechanism over soda can and table, which gets converted to soda can and table, while we reason over the fact that we need to set down, so pick up and place both come inside. So here are some statistics. We have at this point 118 generation templates that we slowly sourced over the last month, different versions of data templates based on error analysis. And using those, we have generated about 57,000 instances for the generative model, and about 70,000 instances for the NER model. The good thing is that with one single program, we are also able to generate more models for the entity, generate data instances for the entity recognition model. And some templates might have very low limited data. For example, objects are hundreds. So when you just randomly place objects and actions, replace placeholders, you can have 2,000 instances of one template. But if a template is like go to a location and there are only 10 locations in the environment, that template would only have 10 instances. So we upsample the templates with very low number of generated instances to have a model not like forget them because of just too little training data for them.
So once we have like the low-level actions that the generative model generates after it's trained on the synthetic data, we have like these granular instructions, like go to the red monitor. Like a complex instruction would be broken down into this. The next thing that we have to do is identify kind of the entities in this instruction with like a very high precision, right? So again, we didn't want to go back to using like pause tagging and stuff because again, the issues that we described previously. So we just trained Distilbert for sequence classification on this data. And since we were generating data, it allowed us to easily annotate the training data with the BIO tagging scheme. And hence our entity recognition module is like a Distilbert module that majorly extracts 6 different entities from the training data from the low level action, which is like action, attribute, object, magnitude, direction, and location. And as you can see, like these are the quantitative results, but these are on the synthetic data, which is like an easy task. And hence we are like quite accurate on the synthetic data. But we also tested this model like in practice, and since our generative model is doing constraint generation, where it's only generating in this particular domain, using just the synthetic data tends to work out well in this case, right? So the next is the verification module.
So the next system component is the verification module. It basically takes in the generative model output and performs some verification on top of it. It consists of 4 submodules, and we'll be covering each of them in the next subsequent slides. So first one is the phonetic match module. As Prasu mentioned earlier, that due to the ASR issues, there were some objects that were incorrectly read, and so to resolve that, we use a phonetically most similar action object in the knowledge base based on the Levenstein distance of the metaphon representation. So this is how it works. So pick up the red ball was one of the examples where it was misclassified as the ball was misclassified as ball. And you can see the representation and their max scores based on the Levenstein distance. And based on these distances, we found that the ball was the most similar one, and we resolved ball to ball. And this is the whole pipeline, how it works in here. The next module in verification is inference module. So in case the end user uses some words that is not in our vocabulary, we use the MNLI model to resolve it to the action object that are already stored in our database or in our knowledge base. So we have chosen the premise for this as the original utterance, and in the hypothesis, we replace the object action pair in the original utterance with the ones that are there in the vocabulary. Here's one of the examples where because the utterance was open the cupboard, but the cupboard was not the object in our knowledge base. So what we did was we replaced it with all the ones, and we checked that there is a synonym of cupboard in our knowledge base, and we replaced it with that. So here are some of the evaluation data that we have. So next a component in verification module is the affordance verification. So we are given a closed set of actions that are executable on any object. And if the user tries to perform an action on an object which is not allowed by the environment, we simply discard that. So here's an example where the user asked to pick up the laser machine, but the laser machine is not a pickable object. So in this case, we directly just discard that instruction. And the final module in the verification is the hallucination check. Since we are using a generative model which can hallucinate information, so in the cases where it is hallucinating, we would want to discard such utterances. So here's an example where the utterance was pick it up and place it on the table, and the generative model gave an output as pick up the banana. And so we just do a check in the knowledge base and the dialog history. If that particular object was not present, in that case, we basically just discard that particular object. Yeah.
Next, I'm going to talk about clarifications and state tracking. So here's an overview of the entire system design for the clarification part. So initially when we get, so like you can follow along my cursor and look at the numbers. Initially, when a user gets when a user says an address, we pre-process it using the generative models and the other methods that we talked about before to extract the action object pairs. But we also maintain a session queue for each of the different ongoing sessions or different games. We enqueue them before sending it to the navigation module. Navigation module is responsible, is the other subteam, and they are responsible for interacting with the arena environment and performing those actions. They also perform some view checks before actually executing those actions within the arena simulator, and then they get a response from the arena simulator itself. Based on the response, they tell us whether the action has been completed or not. So we dequeue few of the actions from our queue. But let's say there was a problem in completing one of the actions, or let's say like there were multiple objects with multiple objects at the same time but with different colors. So we need clarification questions in that case. So they will also tell us, they also send us an error code based on which we generate a clarification question to the user. We get a response from the user, and then we have an extractive QA module, which I'm going to talk about later on, which extracts the answer of that particular question from the user response. Then we peek the last action that we have in the queue. Using the answer and the action object that we have stored in our queue, we enrich that previous action, and then we send this enriched action back to the navigation module to let them perform the action again. So this is how the flow looks like. And these are a few points that to note, like we maintain a separate queue for each of the different game, and since there is no signal from the simulator side itself whether a game is ongoing or whether it has ended at any point, all the calls are completely stateless. Since it's a REST API call, we do not know when a game is ended or when it has started, so there's no way for us to decide when to create a queue or when to delete it. So like we do it on demand. We just assume that as soon as the queue is empty, the game has ended, and we delete it. In case it hasn't, the game hasn't been completed, we recreate the queue. But like there is no problem with that logic in the system itself. So, and also like one last thing is that navigation module doesn't, do any state tracking. We do all the state tracking through the session queue, and based on the, enriched action that we get, we send that action to the navigation module as well as the other things that we have in the queue along with that enriched action, so that they can perform it in one go or multiple go as they wish to. Okay, this is just like just a zoomed in view of one of the scenarios of clarification. So in this case, based on the image segmentation, we see that there are two monitors of different color. So like navigation system sends this error code to us. They send us the expected answer based on what they see and the object in question. We generate a question. This question generation right now is rule based on the clarification type, output that we get and the options that we get. So the question here is going to be, what is the color of the computer, blue or red? Then we expect a response from the user of the sort, the color is blue. Then we use the EQM model, which is the extractive QM model, to extract a single word answer from this user utterance. So the EQM model use the question that we ask the user as the input as well as the response as an input to extract the answer. Okay, so after we get a one-word response from our system through the EQM model, we do a fuzzy match with the expected answers that the navigation module sends us. So in this case, it's going to be red or blue. If there is a match, then we know that a response is what we expected, and like we can continue performing the action. We enrich the action and send it to the navigation module to perform it in Arena. If there is no match, then we ask the question again. So in that case, we say something like, sorry, I couldn't understand what is the color of the computer, blue or red. We inquire this again. So this like loop of asking the question again, if you don't get a correct response, happens 3 times by default. But the user in between can also say stuff like forget it or stop doing that to break this loop if he or she wants to perform some other action instead. Here is a small demo. Since audio is not working, I'm going to play the video here, and then as soon as you're going to use my laptop.
Go to the shelf and place the soda can on it.
Is the color of the shelf you are looking for red or blue?
It's blue.
Done. What next?
Okay, so in this case, we can see that it asked the clarification question, but in the initial utterances, the things that we ask the bot to do are like twofold. We ask the bot to go to the shelf and then place the object. It actually remembers that it has to place the object as well, based on the queue that we have. So like it also does that after it receives the response for the clarification question. Okay, this is the QM model that we use. We use a pre-trained Roberta on squad dataset. And after we get this, after we get the response from the Roberta model, we also have POS tagging for like the response that the model outputs. Then we remove the articles and punctuations from the output of the Roberta model. And based on the evaluation that we performed on the synthetic data that we talked about earlier, we got an F1 score of greater than 0.9. This is again the same example that I talked about.
Okay, so as you can see, our dialog management is composed of very sophisticated and complex systems. So you may wonder, is it very slow to run all of them? So we have the same question. So we run a latency profiling for, we run a latency profiling for each of the module we have. So in the order of our pipeline. So we can see most of the models and modules can finish within 20, 30 milliseconds, except for the generative model, which is the largest and most complicated model, which will be finished in more than 200 milliseconds. So in total, here's a typo, it's actually 377 on average milliseconds to finish every module in our pipeline. And in many of the cases, the user will say very short instructions. So we have a rule-based module called first responder, which will cache all the short and very frequent instructions from the user, and will just return the results right away. So it will skip all the models we have in the middle. So yeah, so it's within 1 millisecond. So in this case, it will be with about 30 milliseconds. So in total, it's really fast, but the whole feedback to the user will be combined with the action execution in navigation team and arena simulator. And also, as you can see, we are working in the integrating with a very large system with Alexa and navigation team. So it's hard for us to test our system end to end. So we have a Dialog sandbox, which we separate our models with the input from Alexa and the action execution from navigation team. So we can test end to end for just the dialogue management models. And we can also design the inputs that we want to test, and we can store the logs locally to analyze it. And we use git diff to very quickly see the changes of our implementation.
All right, so that was whole details of our every model that the dialogue management system has. Let's look at the official results that we gained out of all our hard work in the fall semester. So first up, as we talked about, there was an internal beta phase going on all throughout November, which ended on 29th of November. And this is the final leaderboard of that challenge, that phase. And we were the top team and we were the only team with the last 7-day average rating of greater than 4.0. And with about 63 game sessions played with our bot in that time. A couple of important metrics here are, if we look at all of the whole beta phase as a ranking, we started quite low in the beginning, and we that's the left hand side is the bad news. We at that was the point when we had our generative model 1.0, and the counterpart navigation team also had quite a bit of issues. But I think what we did very well was we responded to feedback that we were getting from users through as the users play the game, and we were able to adapt to it and add in quite good revamps, both major revamps as well as minor low-hanging fruits. So by the end, the whole phase was dependent on the last 7-day rankings. So by the end, in the last 7 days, we were number one throughout the for the whole phase. And another thing here is that the conversations per week have also increased through November. So when we were getting higher traffic, we were actually performing better. A quick shout out to Professor Jonathan Bisk, because these charts are from his data science seminar slides. So another quick thing that we noticed throughout November when users were playing with it was how lexical variations have been shifting. So as we move on in the Amazon Simbot challenge phases, first, there were beta testers who are kind of more knowledgeable about NLU systems. And then there are more general purpose users. And right now we are in a general availability phase where the skill is available on the Amazon store. So more people who are completely unaware of how ASR or language systems work, those people are now playing with the game. So that means that we are seeing more and more lexical variations in our recorded logged inputs, and more fluid expression, which has sometimes seen frustration and questions also. So for example, Alexa, a user said, go to the freezer in the break room and open it. And when we, for some reason, couldn't open it, then the next instruction is just, why didn't you open it? And in case we asked a clarification and we repeat asked a clarification, as Nikhil mentioned, we asked it 3 times. If we are not able to get it, the user just said, I already said it right now, why can't you get it? yeah, these kind of utterances were not present in the internal beta phase because we think that's because more skilled users were using it. This is a graph of new trigrams that we saw in the last month. As you can see, that like obviously we started logging on 9th of November. That's why we don't have data before that, and we have high bars in the beginning. But as you can see, while the new trigrams are obviously going lower because we have seen a bunch of data in November, we're still seeing about 200 to 200 utterances in the last week in this week of December. These two are off days, like the Amazon Simbot challenge had a downtime, but on 7th December and 8th December, we saw again a bunch of new trigrams. So our goal is to have adapt to these and look at new trigrams and figure out if our models can work with those, and if not, then what are the ways to improve upon them. Another interesting metric from the official results that we have from internal beta is the median and the 90th percentile timings that our bot took to complete the challenge. So as we can see, when we were getting ratings of like 1 or 2 at that time, even though our median minutes were still like about roughly 6 minutes, our 90th percentile minutes were close to 15 or 20. And what that points to is that in many of the cases, users were having to say very simple instructions like move forward, turn right, now do this, in order to complete a game. And while we are and as we improved our model through our host of models throughout November, we were able to close the gap between 90th percentile and median. And a lot of this was because of major revamps in terms of new generative models and NER models and synthetic data generation. But a bunch of this, and that's right before the last 7 days, right before 25th, what we did was we only did practical, quick and low-hanging fruit kind of updates and did not make major changes. And we put a code freeze on our whole system on 24th of November because we didn't want to update or put breaking changes in our system in the last 7 days, because that was the main part of the challenge. So a quick overview of the practical updates we made right before the last 7 days. First is ASR replay. So a lot of times when ASR issues happen, like we saw when the user said the color is red and the model understood, like the ASR gave us bed. Instead of, we used to say, sorry, I don't understand. But in those cases, the user doesn't get any information of why the model did not understand. So instead of that, we now say, sorry, I couldn't understand bed. And that way user gets immediate information that, hey, the system actually heard bed instead of red. So they know what exactly to repeat. Second thing is dialog prompts. So if we are in a place in the game where we can easily tell the user that, hey, you can do this, we think that dialog prompts actually helped a lot, because a lot of the users were not aware with the capabilities of our system. They did not know that they could say something like go to the robotics lab and then pick up the cake from the table. Our model can handle that kind of complex instruction and break it down into 3-4 sentences and execute them all. But the user would try to do something like go to the room and then move forward, then turn right, move forward. So just by telling them like, hey, you can try telling me this in order to perform this action, they were able to learn, adapt, and we were kind of able to teach the user how best they can use our model's capabilities. And the final thing, which I would like to clarify, is something called first responders, which as other teammates mentioned, it's a rule-based system, but I want to clarify here that it's not a heuristic or it's not code. It's not heuristics based on code. It's just a caching mechanism. So we only maintain a dictionary of very frequent short instructions of lengths less than 3. And if those instructions come, then we just return the output from that cache, and there is no heuristics to it. And this is only intended to reduce the inference time of the co-reference plus generative plus NER models to less than like by about 300 milliseconds. And I would like to acknowledge Professor Jonathan Bisk, Daniel Fried, and also Jimin for their help throughout this project.
Yeah. So as you can see, throughout this project, one of the things that we have been able to learn is like we have been able to get hands-on experience on firstly, good software engineering practices, develop like an NLP system end to end, which comprises of several different models, and then learn it and iterate about like these, like about the failures and the places where these models fail, and then build and improve upon them. This has again, be like we because of the fact that we were systematic in logging all the failures and learning from the user feedback, we could formulate like why we would need a generative model and why we would need like a better class of models. So that is again, that's just been a lot of good team effort, and good practices that we have followed throughout. So yeah, I guess coming from like the place where we were like at a rating of like 1 and then reaching right to the top of the leaderboard, it's just been like the journey has been amazing learning experience for all of us, and it's been amazing working as part of this team, collaborating. Thank you.
All right, thanks, guys. Yeah, so this is obviously a huge effort that you guys put in, and I'm glad to see that it was rewarded with some actual achievement at the end. We've had students work on Amazon challenges in the past where there was a lot more engineering and integration and not as much science. So I think that's really a wonderful story here. The thing I really liked about the reflections is that it wasn't like there was one magic algorithm that did this. It was really a very sophisticated component-based architecture with multiple options at each step of the way. And that's actually the way that real world stuff happens. So I'm glad you guys had a chance to experience that. I found your assertion that you learned and practiced, great software engineering, pretty humorous, because usually when teams are working on a leaderboard, software engineering and well-organized code is like the last thing on their minds. But you guys wouldn't have survived or done as well as you did if you started out without being well organized. So maybe you had to do a giant refactoring somewhere in the middle that you didn't talk about very much. And I know the switch, of the arena was like a big deal for at least, some members of your team. But what you presented looked like something where you had literally designed all of this in the beginning and then just fleshed it out, which I think is pretty impressive for something this massive. A few, practical points about the presentation. If you were going to make a presentation on this to someone else who wasn't already kind of familiar with the domain, you would want to sort of tighten a few things up. You had a few places where there was some redundancy, so changes from spring followed by the timeline of redundancy in those slides. You teased me with things like intermediate generative model and first responders very early in the presentation, and I was like hoping you explain what they were. By the end, you did explain them. But that kind of thing can distract an audience. In this case, one possibility you would be to have a very simplified version of your architectures for each of your parts. And then as you get to the end, you kind of open up the detail and show there's actually 3 things inside this, box. You did a great job with the system design diagrams. I felt like they were actually not hard to follow, even though I didn't quite know what was in each of the boxes at the beginning. Oh, I had a question about the static knowledge base. How complicated was that? And was that provided to you guys by Amazon, or did you have to build that?
It was mostly provided to us as a PDF document, where
Okay.
where they just mentioned that, hey, these are the objects, these are their affordances. We actually used it by performing OCR,
Okay.
and then once we did that, we also noticed that there were quite a bit of mistakes in there, and they were not just spelling errors because of OCR. There were actual issues with the objects themselves, and after playing some games, we realized that some of the objects, like a microwave, was toggleable but not powerable, which did not make sense to us. And so we actually ended up going through the whole thing and fixing affordances for different
Testing.
objects.
Okay. So to make sure that it was actually consistent with the actual environment. Okay. And then, so what did you do? Just build like a big table with all the information?
Yeah, it's a JSON file.
Okay, great. So there would be some cost in kind of creating that for a new instance, or you might have to have another Explorer module in your system that would actually go around with the camera and, you know, ask the user what all the objects are if it couldn't, you know, look them up in a visual dictionary or something. Okay. Was the toxicity filtering being tested in the evaluation environment? Were some of the users really swearing, you know, trying to break your system, or was that mostly like a requirement that Amazon wanted to have before they would release it into the wild?
So yeah, I think from the logs that we had, the general users and beta testers rarely used anything toxic, but it was like kept as a first check, you know, by Amazon, just so that if they respond with something toxic, we shouldn't repeat that back to them, or you know, like because that's like gets into legal issues and other stuff. So
it was a requirement for the skill certification itself.
Okay, got it.
So we have to
And another thing to add to that is that there were other legal considerations also, like things like who built you, and if we respond something like, you know, CMU built me, or like that's not allowed, because the user should not be able to identify who the system that they're ranking. So as part of skill certification, they made sure that we are not responding anything to these questions.
Initially, we were thinking of building a chat module as well, so like answer out of domain questions with like finding numerous content, but
that would be non-compliant.
Stick to.
But what about the interesting follow-on of why did you do that? Okay, so you remember you had an example where the user was actually asking why the system responded the way that it did. Was that considered out of domain also? Okay, so you're not going to answer that.
We would just say, sorry, I can't understand that. Or in fact, the most humorous we go with that is like, my brain cannot process that. Please try saying something else.
I see. Okay. Very good. So you had a nice table in there where you showed the different co-reference phenomena and then how you handled them. And I was wondering if you actually quantified the relative frequency of the different co-reference phenomena that you mentioned there. Or was it just that you kind of noticed these and then you had to handle them all?
So this is something that we tested on, like it wasn't from the actual testing results or the logs that we observed from how people use it, but like
on the side,
on the side, this is how we tested it, because we didn't do any quantitative analysis of how the model is performing since we were using a pre-trained model. It was just a qualitative analysis of all the things that the model
The only reason I'm asking is that the module that you picked to do co-reference may have been trained on like a different distribution of co-reference phenomena that might be occurring in your dialogues. I guess if it was an issue, you would have figured that out.
Yeah. So that's why like we just tested it thoroughly. Until date, we haven't found any major issues with it that the model wasn't able to handle, so we stuck with it.
Great. I really enjoyed the detailed discussion of the different approaches that you guys took for the action sequence generation. It's like a classic, you know, climbing, you know, Occam's ladder, you know, kind of a thing. Really enjoyed that. On the slide where you had the average latencies, the total average latency didn't add up from the component level averages. And I'm guessing that's because not every component was called in every dialogue, and that the total average was for all the actual dialogues, but not the average latency.
That's
of
exactly.
everything.
Yes, that's the end-to-end latency that we have.
So maybe if you show this to somebody else, make sure you take the time to explain that carefully. So the dialogue sandbox is obviously a really smart idea when you're in a sort of turn the crank really fast competition mode. But how sophisticated was it? So did it simulate navigation failures, or you guys would have no way of knowing whether something that you were passing on would actually come back okay? You just said, oh yeah, okay, ready for next instruction for everything that you sent?
Yeah, so because we were working in a fast-paced agile development environment, and there is another Capstone team working on the navigation side of it, we did not simulate that. We basically just said that if we are able to produce a good action sequence that the navigation team should be able to handle, then we don't need to do anything more. And there were other, like we just tested our, in case navigation team sends us an error code for clarifications, for example, we used ad hoc approaches to test those failure cases.
And
so the summary is, because you were doing action sequence verification already,
yes,
you're reasonably confident that the downstream guys should be able to handle that, so you didn't bother. Okay, I think that's the right trade-off.
And one of the most important reasons why we had to develop the dialog sandbox was because of end-to-end testing, because we were changing so many different models at different points of time. Once we plug those models in, we wanted to ensure that the end-to-end testing doesn't break, because there can be some causal relationships between some models, and then there can be a waterfall of errors. And the dialog sandbox actually allowed us to verify, every time we introduce a change, we know that we have a certain set of instructions that used to pass earlier, so we can verify on these if these keep passing or not. So it's like a good integration check.
Okay. I think two main reasons were that when we are just in that mode of running our test script with a bunch of it has about 150 examples that we test coverage on. So if we're running that script, we don't just want to bombard the Amazon orchestrator. B, because we were in an agile development environment, the navigation team also was sometimes changing their code, and there would be cases where their things would start breaking and we would not get a good response. So we wanted to be able to test our things in isolation without being dependent on navigation.
Got it. Okay. Anybody here in the room have a question? Okay, anybody on the Zoom have a question or a comment? John, Jonathan, Benny? All right, great. Well, thanks a lot, guys. Amazing effort. One of the things I'm going to have to discuss with Jonathan is sort of how to generate a news item from this. Because usually, when we have a team that wins a leaderboard, we work with the public relations people at CMU, and this is sort of good enough to get out of LTI. So we'll probably have something on the CS website as well. So you'll probably get an email from us on this. Probably some of you will have to provide quotes, whatever. I'm guessing Jonathan's done this before, but I'll help out necessary. This is definitely the kind of thing you want to make some noise about. Do you guys win anything other than just glory, or is it just glory?
So the challenge is spread out over 2 years.
Okay.
It started half a year before the capstone started,
I see.
and it goes on half a year after it.
I see.
So the right now, after the internal beta, the competition has entered the GA general availability phase.
Okay.
And after that, there's semifinals followed by finals, which will basically happen in March and April.
I see.
I
So,
think
so there's like a massive grand prize at the end of everything. Huh?
Yeah, I
Yeah.
think it's like 500K or something.
500K for the winning.
Oh,
the-
Yonatan, we have to have a meeting.
so-
Yonatan said in the chat that he's not able to actually talk where he's at, so that's why he's being silent. So he still loves you guys. Don't worry.
so these three phases are left, and I think one thing here is that I'm like at least one member, me, I'm here for the next semester, and I've decided to work on it throughout till the final space with Professor Jonathan.
Good. Yeah, I think the question is whether we, want to get another team of CBS students helping out. And I'm obviously really open to that because it's a big challenge and there's a lot to do. And if you can use more, people, let me know. But Yonatan told me he would have a conversation with me about that.
Yeah, also, Professor, I would also like to point out one thing. So you remember in the midterm presentation, you had suggested synthetic data generation.
Mhm.
Well, that was actually one of the main things that helped us in this competition. Because we did synthetic data generation, we could train like the generative model to not hallucinate, and that actually replaced all the older rule-based models. And then we also could train like a entity recognizer, and that kind of improved a lot of
Yeah, I'm
things.
glad to hear that. And in fact, I was impressed by the use of the generative model. Because in general, I think people still think of generative models as being not so great, but for this particular purpose of generating, a sequence of smaller instructions, it's like brilliant, to think of it that way. So I'm glad that the data synthesis allowed you to get there. That's great. All right, any final thoughts before we wrap? All right, thanks, guys. Great job. Very enjoyable.